regardless of that, all right? So welcome back. Today we'll continue on with the topic of pipelining. Anyone heard of this technique before? So I motivated using doing laundry example from Tuesday, right? Which is, let's say you've been working on our assignment and having a lot of fun with it. I also noticed that people are having like weird definition of fun, good and bad thing. Anyway, so I'll tell you the backstory about that word after this class. Pipelining is basically the method you can kind of like stage what you do, stage your operation, so you can kind of queue up more operations and share so that they can share the resources, right? So let's go back to our basic design we have from Tuesday. Again, the key things here are you have the fetch unit, which basically go to the memory and fetch the instruction, right? You have the decode unit, which takes the instruction and basically figure out what am I supposed to do with this instruction. The decoder basically sends a control signal everywhere on your CPU. Say, if I need to run this instruction, make sure I take the data from here, make sure I take the data from there, add them together or subtract them or multiply them depending on the instruction type, or I need to go get data from the memory or whatsoever, depending on the instruction. The decoder would handle that. All right. Then there's the execute unit, which is the ALU that performs the instruction. Then there's the memory, which these days actually getting a lot more important because everything else here is quite possible. I would say it's not easy, but it's possible to make it faster really rapidly. Your CPU gets faster quite quickly compared to your memory. The memory becomes like the slow guy, which is, yeah, I know I can get faster, but I don't get faster at the same rate as the CPU. So the speed kind of having this bigger gap, bigger gap, bigger gap, right? So memory becomes another important part of the CPU design. How do we handle that? Then that's the last step, which is, okay, I'm done with the current instruction. What do I do next? Do I go to the next instruction, the next line, or do I jump somewhere else? All right. And here's the question. In the multi-cycle architecture, I said that you can use multiple cycles to add or to multiply, right? So that way you can clock faster. And while you're clocking, if the add finish first, it's okay. Our CPU is faster. You don't have to clock it so that it's, think about it this way. This whole thing determine your critical path, that whole thing. If you don't do multi-cycle architecture, that whole thing determines your critical path because you need to finish the whole thing. Now, with multi-cycle architecture, you can kind of like stage them and say, okay, the first cycle just fetch, the second cycle just decode, the third cycle just do the first part of the add, the second cycle maybe handle the upper bits of adding, right? Because let's say you add 64 bits, it might take a few cycles, right? Here's the problem. When I fetch something, right? What are the active parts? The wire that go to the memory, right? Because I have the PC saying, hey, that's the address I want. The wire that come back from the memory say, that's your instruction. And that's it, right? If I go back to this diagram, the active parts of the fetch are these two guys. Anything else are active here in the diagram? So do I end up with quite poor utilization of my hardware? Because I'm trying to fetch right now, right? And while I'm fetching, I'm not doing anything else in the other part of my data path. By the way, this whole thing, there's a control path and data path. Data path are the hardware resources, right? They're not doing anything. They're waiting for the data to go into the decoder, right? So when I fetch the decoder, the register file, they're idle. Idle means that they're not doing anything, right? And while you decode an instruction, the fetch unit is idle, the register is idle, the ALU is idle. While you execute, the only ALU is active, right? So the idea is actually motivation. Is this a bad thing? Let's say you're working on a group project. Let's say you're working on a group project with 5 people. And while the first person is working on a part of the problem, everyone else are like, I cannot begin until you're done. Then the first person gives the job to the second person, and everyone else are like, I cannot begin until the second person is done. The first person also now not doing anything. Is that a really good project design? Not at all, right? Why bother having 5 people? You can probably run the whole thing, the whole project with one guy, right? In that case, there's no need to have 5 people at all because at any given moment, only one of them is active. Similar idea here, right? Well, we have a lot of hardware, only a fraction of them are active. The idea is, well, let's say my instruction is decoding, can I pump another instruction into the fetch? Now, quick question, is this a good idea? Second question, is this more complicated? What could be the problem? Let's throw some brainstorming out here. Yeah, you have to track. Basically, let's say you have 4 steps, right? Let's say your instruction has 4 steps. You need to track where I am. Am I in the decode stage or am I in the execute stage, right? What else? What if you have a branch? What if you need to jump somewhere? You don't go to the next line. How can you fetch? Because you don't know where's that next line, right? Let's say you have an if else and your program is running. And do you have a way to predict where your if else are going when your program is running? Let's say you as in a computer, not you as a programmer. The computer are running your program right now, right? And it's trying to track all these data. But here's the problem. Let's say I have something like this, right? If X is less than Y. This class has 2 steps. What's the first step? Definitely get X and Y. Then compare. Then branch. So if you think about it, there's at least 2 instructions. Compare, then branch. I can put compare in my pipeline, right? I can start the compare. But depending on the result of my comparison, I don't know where I'm branching to. Do I take the branch or do I just go to the next line? Now you see another problem, right? When I try to do pipelining, because here's the thing. How early can I know the result of my comparison? Until I hit the ALU, which means I have been through the fetch, I have been through decode, then I'm in the ALU. Then I would assume I kind of know the result, right? And what do you fetch until then? Right? The question is, until then, what do you do? Right? So that's another possible problem that we're gonna run into. So we're gonna talk about the first problem, which is how do you remember where you are today? We'll handle about branching next week on Tuesday. All right. Now here's the basic of pipelining. I would simplify things by let's do laundry. You have to wash, dry, and fold all the clothes, right? So let's say your washer takes 30 minutes. Your dryer usually is longer, so let's say it's 1 hour, and you take 30 minutes to fold everything. All right, so that's your task. One instruction, you have to wash, dry, fold. All right. If you have multi-cycle architecture without pipelining, and you have to finish washing 3 batch of laundry, how many hours do you take to finish the whole thing? 3 batch of laundry, multi-cycle. We don't pipeline. So that would be 3 multiplied by the total time for the whole instruction, which is 2 hours, right? So that becomes 6 hours. So the question is, because you guys are smart, how do you finish this faster? Let's say you have batch A, B, and C, right? You would throw batch A into the washer. right? Then when A is done, you throw them into the dryer. What do you do next? Yeah, right? And here's the problem. Well, not a problem, but here's something you have to kind of consider, right? At this point, at 1.5 hours, the first batch is done drying. The dryer is free. I can fold them. I cannot start drying the second batch until 1.5 hours, right? And I can fold it here. I can wash it here. I mean, I can also choose to wash it here and have some place to like put the soggy clothes, right? And then I can dry it here, throw it here. All right. So that's the concept of pipelining. The total time here is 4 hours. You see why it's 4 hours? Because dryer for each of them is 1 hour. That becomes a bottleneck, and then you have the washing and folding at the end. So it's 1 multiplied by 3 plus 2 multiplied by 30 minutes. So that's 4 hours. Here's my next question. If I know that dryer takes a long time, and let's say your family is like have multiple people, you ended up with a lot of laundry to do. What would you do to fix this and make it a better design? Let's say you have more money, what do you add? The drying machine, right? So it's the same thing here about hardware design. It's about the cost of adding things and what's the benefit here, right? If I buy more washing machine, do I get the benefit? Not really, because the bottleneck is kind of the whole thing is bottlenecked by the number of dryers. So I can add dryer, right, to gain extra drying machine, and now the whole pipeline will be fully utilized, right? Now, with the process of design, let me define the pipeline this way, right? I said the first step is I fetch the instruction. Second step is decode. Third step is execute, memory. Then the last step is what we call write back. Write back is basically when I'm done with everything, I just need to write the result back to somewhere, like a register file, right? Update something. Update the program counter, for example. All right. Any questions so far about our pipelining strategy? All right. Seems simple. Now, here comes the problem. You see how this wire from here to here is a single wire. What do we know about wiring? Let's say that wire has the number 24 right now. The whole wire, if you measure the value, it will be 24 everywhere. Huh? Oh, so when I have a connection between two components, right? The way I would connect them in hardware is I wire them. I put wiring between two components, right? And if the first component, like my instruction register, program counter wants to, yeah, this should be PC. My bad. Didn't realize I have this typo for a long time. This should be your program counter. Let me change color. Instruction register store your instruction, so that's where you fetch into. All right, my bad about that. This is a program counter. Program counter say, hey, I want to fetch that address. It sends the address through the wire to the memory, right? It makes sense. I want that address, so I send the signal through the wire with the address inside the signal. So the signal is the address, okay? Now, the memory got the address, takes the instruction back. My problem is when I'm doing a pipelining design, how many instructions can share that wire? More than one. Let's say I'm fetching. Let's say right now instruction 1 is here. I am done with fetching, and right now fetch is in instruction 2. Instruction 2 is fetching right now, right? It basically means that I have one program counter. So what value does it take? Should it take the old value from instruction 1 or should it take the new value from instruction 2? Why would that matter? How many people use exception in your code? Not much, but you use it. All right. Anyone else use exception in their code? You read exception before, at least, right? Or you've seen exception before. Might be your code bug, like divide by 0, right? Now, let's say divide by 0, when do I detect this? In the ALU, right? I will not know it's a division until I reach the ALU, and then the ALU will say, hey, that's weird. I cannot do divide by 0. So let's say instruction 1 is in the execute stage, right? What does exception do? Stop the process. And you have to handle that, right? The thing is, if I want to stop the process and resume right after divide by 0, so divide by 0 instruction 1, the one after divide by 0 is instruction 2 in the decode stage. The program counter has instruction 3, right now. How do I resume? Instruction 1 PC, right? So you need, basically, the question here is, how do we store this intermediate value, right? You got my problem here. I have multiple instructions in my pipeline. Some place has instruction 1, some place has instruction 2, some place has instruction 3. And many of these components are combinational logic. It's designed to handle only one instruction in the whole design. So the solution has to be this. I need to have intermediate thing to store instruction 1's data. Then I have to have intermediate things to store instruction 2's data. All right. Otherwise, I lose progress. Another example. Let's say instruction 1 is in the write back. Instruction 2 is in the memory, right? Instruction 3 is in the execute stage. And let's say all of them are like add, right? Instruction 1, I want to do add R1 plus R2. This one, I want to do R2 plus R3. This one, I want to do R4 plus R5. See the wiring between the output of my ALU, the data, the one that I labeled data, they are being shared by 3 instructions. How do I make sure that in the write back that wiring has R1 plus R2? But the one that has instruction 2, that part of the wiring has instruction that do R2 plus R3, which is a totally different value, right? You need intermediate storage. So what is the storage we can use right now? Over here, anything that can store data, except for a memory. Memory is too far. We don't use that. The register, right? So one of the idea in pipelining is for every single steps here, we would add this unit called the pipeline register. It's not the same as register file. These are things that the programmer doesn't see. These are internal inside the hardware, and it's designed to store this intermediate temp value. All right, so here's the key issue. Each stage is handling different instructions. This means that the design needs to somehow, right, magically process 5 different instructions using the same hardware, right? Fetch is instruction n, right? Decode instruction n minus 1, execute n minus 2, memory is n minus 3, write is n minus 4. All right. And these are 5 different instructions. One of them might be adding, the other one is subtracting, the other one is like load and store, the other one would be like jump or something, right? It doesn't have to be the same instruction. And even when they're the same instruction, the data are different because you already finished the first one. From the programmer point of view, your assumption is I run instruction after another instruction, right? And the programmer should only see the write back. Because of this, your assumption when you run assembly code, right? each individual line that you see are atomic in a sense that you finish that thing before you move on to the next line. Why is that a useful thing? Simplify your debugging experience, right? So far in this class, your debugging experience has been like abused to hell, right? Imagine you have to like debug assembly and your assembly code can somehow crash in the middle of the instruction. Not fun, all right? So the solution right now is I just want to make sure the programmers see the instruction get up, the state get updated after the write back. Anything happen before the write back, programmers should not see that. It should see the update only after the write back stage. All right, with me so far? Now, this also means that anything that in the fetch, decode, execute, and memory will have to be in some intermediate buffer inside the hardware that store this temp data. All right. And we can use this thing called pipeline register for that. Well, it's a buffering area implemented almost in a similar fashion as your register. Sometimes cheaper, to be honest, because we can kind of make it cheaper. But the idea is I can buffer intermediate value between the steps. All right. Usually there'll be one for the fetch, one for decode, one for execute, and one for memory. In a deep pipeline design, like your laptop, which has, I would tell you your laptop has more than 30 stages. Yeah, that's how deep the pipeline is for your laptop. That's why you can clock it so fast. The thing is, with 30 stages, it means I need 30 sets of these things, right? And that's okay. That's okay because the benefit is really pronounced. Like, it's really good to have this. All right. This can be costly because it does incur additional storage, right? It's the argument about performance versus power, and performance versus how big is your chip. The only instance that you still see a simple pipeline that looks like this, which is sometimes 5 stages like fetch, decode, execute, memory, write back, or 7 to 9 stages are the microcontroller that goes into like these devices that you see, like smart things, right? Those are really tiny chips, and you don't need performance that much. They just need to make sure it runs, right? But for modern computing devices, the number of stages is really deep. Now, the blue thing I draw here again, sorry about this, should be PC program counter, right? And then the IR should be here, instruction register that store my instruction. So the decoder, the execute unit, memory, write back, and the fetch has its own basically barrier between the two stages that store, think of this vertical red line as a buffer. Okay. Whatever data that cross that line, I store them in this buffer. For example, again, remember I do R1 plus R2 right here, R2 plus R3 right here, and then R4 plus R5 right here, right? Because I can. Now I can. Because when I'm doing R4 plus R5, I'm basically trying to write it here. And in this cycle, if I have the voltmeter and measure the voltage right here, what value do I see? At this point, what should be the value that I measure? R4 plus R5, right? Because that's the instruction I'm doing right now. This is a buffer, so this whole line right here, if I have the voltmeter and I measure the voltage here to see what's the value here, should I see R4 plus R5 or should I see R2 plus R3? It should be R2 plus R3 because the pipeline register, this guy, is a buffer. It's like when you have a temp variable, and whenever you clock, you write the new value into it. So the way it works is when you clock, you take the input, you store them. So right now, the input to this pipeline register is R4 plus R5, but it's storing R2 plus R3 right now, which also means it's giving the output R2 plus R3. So that way, the wire that comes out of it will measure R2 plus R3. Once I clock, R2 plus R3 is gone. R4 plus R5, which was the input, go into the buffer. Basically, when I clock, the instruction move one step, right? So in that case, R2 plus R3, which is now the input to this guy, into this pipeline register, will not be inside the buffer yet. Inside the buffer, you're going to see R1 plus R2, right? You're going to see R1 plus R2. So the wire that is now connecting all the way to the register file to update the actual output of your instruction will measure the correct instruction, which is doing R1 plus R2. When you're clocking this guy, this instruction is done, gone. The next instruction, which is doing R2 plus R3, will move into the write back. So that way, it's kind of like it's a queue where you move one step after another, right? And the pipeline register acts like a buffer that replaces the old value every time I clock. And for whatever value I'm remembering, I basically will output that value for this cycle. Yes.
So what do you mean by
when I clock? So the way your CPU works, right, is because wiring can hold one data. So if I want to send a sequence of data, I need to separate them by a clock. So I would flip the clock from 0 to 1 back to 0. So 0, 1, 0, that's one clock cycle. When I clock, everything moves. Everything moves. So remember from the lecture on Tuesday, we have architectural state 1 to architectural state 2. Basically, you move from state 1 to state 2 within some number of cycles. So when you clock, you're moving instruction from the earlier stage into the later stage, essentially. And the clock signal are actually another wire that connects all the components. So all the components are built so that they are aware of this clock. And whenever the clock goes to 1, it looks for the time it go back down to 0 again. And when it go back down to 0 again, the hardware updates the whatever it has to do that are buffering right now with the input. Yeah.
So it's like a mutex?
The what?
One.
Is it like a mutex? You can kind of, well, it's not essentially a mutex. It's like, it's your, let's imagine it this way, right? You're writing a program, but your program, the way the program works is everything happens together. The only thing you can do in terms of sequencing is you move the clock. And then the input will come from somewhere. And when you move the clock, the sequence of input will flow in. Your hardware will compute everything you design for that clock cycle until it hits the end, which is the buffering area for the next step. And when you clock, the buffering area would take the input, replace the old one, and it keeps doing this. Not sure if that's a good explanation. So the quick answer is this whole design, if you do not have the clock, it can handle one set of input. The whole output will be just based on that one set of input. And in order to feed the next input, you need to separate the two inputs, right? In sequence, in time. And the way we do this in your digital design is to clock them, because each cycle specifies one sequence in time, so that you can have the sequence of time, so you can organize the input flow that comes in and expect the output flow that would come out of your design in a sequential pattern. All right, so the next question you might have right now is, why do I have to do fetch, decode, memory, execute memory, write back? Why 5 stage? All right, my simple answer to that, textbook answer. If you read textbook, we always do it this way because it's simple. Each stage do one task. In reality, I can divide the fetch into multiple steps. I can divide decoding into multiple steps, right? For example, remember assembly question from SuperScale, the push kill question from assignment 4, task 2. The one that say, if you see these bit pattern, it becomes push kill with this format, right? Imagine how decode cannot be done in one cycle unless the design is really big, because you need to compare multiple things. Am I reading 1 byte? Am I reading 5 bytes? Right? Am I reading 4 bytes? That part alone is likely cost one cycle, because you need to read the first byte, then figure out how many more bytes am I reading, right? So in that case, decode makes sense to have multiple clock steps in the middle and have multiple stages, right? So modern design have a deep pipeline. Fundamentally, they're basically slicing this fetch, decode, execute, memory, write back into something more fine-grained. Fetch 1, fetch 2, fetch 3, decode 1, decode 2, decode 3, right? What's the downside behind that? Why do I not want to do it sometimes? It actually makes the chip bigger. Sometimes if you have a device that's like your projector remote, right? The chip is likely to be that size, like really tiny. And you want to make it cheap, right? So you don't want to do deep pipeline. As I hit the button, it works. That's it. That's my requirement. Why do I pay 1,000 baht for something that would cost me like 100 baht, right? That's actually, by the way, that's a job of an engineer. Make things cheap but still functional. All right. Okay, so let's go over our earlier example, which is like a bunch of these instructions, right? And let's assume 5-stage pipeline. So what we've seen earlier is called a 5-stage pipeline. If you have a deep pipeline, it becomes N-stage pipeline. For example, many of your Intel, AMD, and Apple M1 chip would have more than 30 stages. So you just call it 30-something stages pipeline, depending on the design. All right. So let's do this example. For the add, right? First cycle in my design, I fetch the first instruction. For sure. That's the only thing I can do. All right. Then I clock the next cycle. What can I do? Instruction 1 will go into the decode step, right? Instruction 2, because fetch unit is not doing anything, so I can fetch. All right. Now the third cycle, I can move this to execute. This is decode. This is fetch. Memory, write back, right? Execute, my bad. Memory and write back. Fetch, decode, execute, memory, write back. So how long does this whole thing take? 8 cycles, right? If I do multi-cycle architecture, let's assume each stage is 1 cycle, means that each instruction takes 1 cycle. To finish 4, it's going to be 20 cycles. What's your speed up? 250% speed up. Is this a good design? Yeah. So let's imagine in the ideal world, right? You have 1,000 instructions on a 5-stage pipeline. Let's say you have 1,000 instructions in the ideal world. How many cycles does it take? 1,000 instructions, right? It should take 1,000 plus 4. Because each instruction can be fully pipelined. So every time I clock, I finish one thing, right? Except for the first instruction, which have to do 4 more cycles, right, to finish. So that would be like 1,004 cycles. So on average, in the ideal world, right, my CPU can finish 1 instruction per cycle, which is the same benefit of single cycle architecture, but now my clock is way faster. Right? Because I don't have to support complex operation within one clock, right? I have a cheap pipeline, And then I got a lot of speed up, right? This is why every single modern processor and microprocessor that you see do pipelining. It gives you such a benefit that it doesn't make sense not to do it. All right. Any question? So imagine your computer has 30, like let's say 30 stage pipeline, comparing to the 5-stage pipeline, which maybe I can clock at like maybe 1 gigahertz max if I want to design a 5-stage pipeline processor, right? Probably something like 1.5 gigahertz. Comparing to the 30-stage pipeline on your computer, what's your clock these days? 3.5 gigahertz, maybe. Four. Nah. Let's say 4 gigahertz, right? Comparing to the 5-stage pipeline. So your 30-stage pipeline, in the ideal case, is likely to be 4 times faster because I just do deeper slicing, which means I can clock faster, right? That's one thing. There are many, many more things that happen on your CPU and the GPU to actually improve this design. All right, but you can see that as we progress to new techniques, your chip is faster. All right, so we are kind of moving from like the 1950 to 1970 now. Well, 1960 to be honest. There are way more things in the 70s, like caching and all those things. There's like early 1980s as well. Then you have like multi-processor idea popping out as well. Now let's assume another different case. Everything looks almost the same, but you have to multiply. All right, to multiply, and multiply takes 5 cycles, so your execute becomes 5 steps before I can finish the multiply. And I cannot pipeline the multiply. Basically, if I am multiplying one thing, I need to wait until they finish before I can multiply the second thing. So how long does it take, right? My point is, do you think this is slower than earlier example? Yeah, obviously, right? Because the first multiplier has to wait for the multiply unit to free up before I can multiply the second number. All right. So modern day computer, this multiplier also get fully pipelined. So that way you have multiply step 1, multiply step 2, multiply step 3, multiply step 4, multiply step 5. So instruction 1, while it's doing the second stage of the multiply, the first instruction sneak in doing the first stage already. Yeah. All right. Any questions so far? You can fill in the table if you want, but basically, okay, let me fill in the table. So it's fetch, decode, E1, E2, E3, E4, and E5, right? Then memory write back. I can fetch here, I can decode here. I cannot execute because it's busy. It's doing the first multiply. I can only send in E1 right here. Now I can fetch here. Decode is being occupied by the second instruction, so I cannot decode until here. Again, resources are not shared. If the second instruction is stuck in the decode, the third instruction cannot use the decode, so I'm stuck there, right? Then I can do XOR, right? Depending on your design, one thing you can do is to execute here, memory, and write back. Then I can fetch here, decode, just waiting for the execute to free up. So you do decode, execute, memory, and write back. And as you can see here, it's kind of longer, right? It's a lot longer. Another thing from this example that I want you to be aware, you see how write back happen in order. if I want to, I can kind of make the design so that like instruction 4, when I fetch, it sneaks in and finish the whole thing before I finish instruction 2, right? Assuming I have unlimited hardware, I can do that. Basically, it means that the write back of instruction 4 is done before instruction 2's write back. Now, let's say you're debugging your code. Instruction 3 caused your program to crash. Instruction 3 caused your program to crash. You're trying to debug it. And it just happened before instruction 3 finished, instruction 4 already finished. How do you feel? Weird, right? It basically means that let's say you run your program has 5 lines. You finish line number 1, line number 2, line number 3 is the one that caused the crash, right? When you debug your program, you're trying to look at line number 3, but when it crashed, somehow magically, line number 2 is not done. Line number 4 is done. All right. So from the hardware point of view, we always make sure write back at the end. Whatever we try to do in the middle, write back is in order. So you see instruction 1, write back. Before instruction 2, write back. Before instruction 3, write back. Before instruction 4, write back. We guarantee that. Otherwise, your job as a programmer is going to get weird. Right? Because it basically means that if something crashes, you don't see the same order that you expect. And it's really going to be really hard to debug your program. All right. So that's one thing I want you to notice, that how basically all design, you have to ensure that at the end of the day, from the programmer point of view, we don't do any optimization. Everything is nice and slow. Right? And then some black box happen, things are fast, but from your perspective, everything happened in order. All right. All right. So what are some possibility that pipelining is not so ideal anymore? You've seen one example already. I have one multiplier and they share between 2 instructions, so they have to wait. That means that in that case, I don't have enough resource to move the next instruction through the pipeline because I'm waiting for the multiplier, right? So the advanced trick is I would pipeline the multiplier, which is what we do in a CPU. You're not going to talk about how to do it, all right? But just assume that this is something that you have to do to make it faster. What are the effects of instruction stall? So whenever you have to wait, we call this instruction stall, because stalling means waiting. So the instruction is waiting because someone is using my next resource, right? Imagine like when you have to, how many people cook, or at least know how to cook, or like cook sometimes? So when you cook, right, you have to have the sequence of things you do. You should not reorder the sequence. That'd be bad. Basically, don't do that. All right. And the thing is, let's say the kitchen is shared between many of your friends, and 2 of you guys happen to be, hey, I want to cook at the same time. All right. You would share the resource. In that case, if the resource is occupied, like let's say the sink is occupied before you're trying to clean the vegetable, whatever, right? The next instruction has to wait. One solution is have to sync. Right? I mean, in this case, we cannot fully pipeline the sink. You can't really stage the cleaning of the vegetable, but you can see the picture, right? These make the second person stall waiting for the first person to finish. And the first person, because they are ahead of you, they have to finish the cooking in sequence. And you can't jump the line by not cleaning the vegetable and go directly to the oven or the stove area to start cooking, right? I mean, I guess to be honest, if it's safe, you can do it. But here in Thailand, I recommend not doing it for health reasons. Anyway, so what can be the case of this? Obviously, not enough functional units. I don't have enough adder or multiplier to support all this like instruction. Sometimes some steps take longer, like memory can take longer. It means that let's say I have 5 instructions, right? Instruction 1, 2, 3, 4, and 5. This thing is add. This is memory. Let's say this is 1 nanosecond. 1 nanosecond. Yay, 200 nanoseconds. What does it mean? It basically means that I don't see instruction for ever. I don't see instruction for results until I wait 200 nanoseconds. It blocks everyone else, right? Sometimes you also have unbalanced design. You give too much resource to something, and then that's not your bottleneck. What do you do when the instruction stall? Here's the goal. Make sure everything's still correct. Make sure the program the CPU is running behave the same way designed by the programmer. If the programmer write a safe program without a bug, it should not have the bug. If the programmer have bugs in them, you should give the bug to the programmer, throw them away at the programmer's face, right? Do it exactly the same way intended by the programmer. Now, here is when you're stalling, right? The next issue is, if I'm stalling, what should my pipeline register output? Instruction 1, 2, 3. Fetch, decode, execute, 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 memory, write back. Fetch, decode, wait, execute, memory, write back. In that case, right, while I'm waiting, there's going to be a pipeline register in the decoder that accepts the decoder input. But I cannot move from the decode to the execute because ALU is busy doing the instruction 1, servicing instruction 1. What do we do here? Any idea? What should I do with the pipeline register? Should I replace the output with the new input? No, right? I should keep the output from the old input from instruction 1 so that execute is still correct, right? So just make sure again, the pipeline register holds the output. So that's the next issue. Make sure that it gives the correct output to whatever needs them. These 2 bullet points, to be honest, sound obvious from your point of view, and it is obvious. The reason I put it there is if you have to design the chip for the first time, this is where most of the hardware bugs on your design will come out because you by accident put the wrong output. I did it before many times, all right? When I was doing the lab, I think, yeah.
How do you know that?
Okay, so most of these register, if not all, will have the right signal going into it. So the way you overwrite the old value inside the buffer is you send the right signal, say, write enable. Then the whole thing will get replaced by the input. Otherwise, whatever input that goes in, if I don't enable the right signal, it keeps the old one. The bug is if I have to do the chip design for the first time, I will miss the right signal at the cycle I have to do. Imagine everything has to be cycle accurate. If I'm not doing it cycle accurate, it means that I write to the wrong guy, right? So you shift right signal by 1 clock cycle, everything goes kaboom. It's like, where is this thing going wrong? So you can imagine that happening. If you want to try that, I do have a lab material for that as well, like a detailed hardware design. In case you're curious, we are not going to ask you to do that. Right now, it's just simulated in C, so it's much simpler. There's no such thing as kind of like the right enable signal kind of thing. You can just say, this buffer is replacing this one. This value replaces this one, right? But that's why we need that 2 bullet points. Because if you mistime the signal from the decoder, right? You send the signal out and you mistime that, you basically send the wrong signal to the wrong instruction. So the programmer will see incorrect results. The next idea that I would touch on, because we're not going to go into the detail of the design, but we're going to touch on because this is actually on your CPU. It's called SuperScale Architecture. It means that if I go back to this example, I have to multiply, right? Instruction, right? So one idea is I want to add more multiplier, right? The second idea is, well, why do I fetch one instruction at a time if I have two multipliers? Why can't I fetch two? Because I'm greedy. And proactively just push two instructions at the same time. You can with the SuperScale Architecture. Basically, it's a design that allows you to have, so you have a fetch unit, right? Decode, execute, memory, and write back. There are this thing called instruction window. And the fetch will always keep fetching. I don't care what's happening in the pipeline, I just keep adding things into the window. Then the decode takes the top one, because the top one is the oldest, right? Take the top one, figure out what to do, feed to execute, and it would kind of aggressively go through the table so that if anything is empty, and if I can feed it to this execute unit, decoder will do it. Yes.
What is the path limit?
Oh, then in that case, pipeline stall. Yeah. Let's say there's a common thing. For example, your code will be like add, right? Then maybe 3 multiply consecutively, right? In that case, you're gonna see add, multiply. If you have 3 adder, 3 multiplier, everything can be feed to those things, right away from the window.
Like our servers buffer, like they just like
Yeah. It's kind of like when you look at like network server, like a server client model, right? And you have the buffering that takes a bunch of packets in, and then whenever the server is clear, they have the worker from the CPU side. The worker comes in like, oh, I'll process this guy. Same idea, right? There are even more ideas that apply. I might do that on the last week of semester to kind of throw in these are additional things that is done on the CPU to make it fast, right? The idea of SuperScaler, one of the key designs, make sure it's balanced. For example, if you only have like 4 copies of your ALU, don't fetch 8 because you're gonna be able to fill in the windows quickly, and your ALU is not, there's not enough ALU to process 8 instructions in one cycle. So it should be balanced. And these allow you to basically finish more than 1 instruction per cycle. So in a traditional pipelining, you can finish only 1 instruction in a cycle, right? But with SuperScaler, internally, we are kind of finishing a bunch of them in parallel. Still need to ensure write back happen in sequence, all right? But internally, your code is already gone to the future. It's just at the end of the day, I just report to the programmer later. It's like when you have a team, your programmer is like the team manager. Internally within the team, you keep going, right? And then at the update, you report to the manager, this is what I did. But then while you're doing the update, when there are also like future progress, that's kind of like a SuperScale architecture. Yes.
how does it maintain order?
That Windows is already ordered. So you know what you have to finish.
But what if
So that window will be like the entry in that window, even in window when you dispatch to the ALU, right? You can keep the entry and you only delete the entry when you're done. So that way you have the order in the window, and the only thing write back do is it doesn't really take into account like at the end, it look at that window and like, are you done? Are you done? Are you done? Oh, done. I retire. Go to the next one. Then just check the top one. It's like, are you done? Are you done? Are you done? Then I retire. Internally, there'll be like multiple done here, right? And then I'll retire one every cycle, and that's okay. All right. We call this, I guess, this exploit. I don't say we call it. I don't want to say we call this exploitation of something. Sounds kind of bad, but this is instruction level parallelism, because your program, the way you program things, it actually internally have a lot of this internal parallelism that you didn't realize. That we can do the second add and the third add at the same time. Why not? Right? Now, what else? Other cause of instruction stall, long memory latency. So how do we fix this? Something we learned from SuperScale. All right. So we can use the cache. We can use DRAM. We can use the bandwidth to hopefully fix it. Branch misprediction is what we're going to cover next week. Remember when I said, if I have if x is less than y or not, right? The code, something like looks like this. If x is less than y, it means that the first thing I have to do is check if x is less than y in the execute stage, and I cannot fetch until I know the result, right? So one thing I can do is I can guess. Maybe I'll go to the if, and I keep going and fetch that direction, right? If I guess wrong, then I stop rerun. We call this branch misprediction. Actually, let's not do it now. I want to go to this part. This is basically the majority of the rest of the second half of the class today. We call it data hazard. And from the name, it sounds bad. And yes, it's bad for pipelining. Look at this example. This is destination, source 1, source 2. And we'll do a quick break right now. I'll keep the slides up. Don't even have to assume anything down there. What's the problem here? All right, with the pipelining design. So I'll pause the recording right now. Take a break. I'll keep this up. You can take a quick look at what's wrong here. Why is this bad for pipeline? All right, so let's come back here, and you already brought up the issue, which is R0, right? It's getting written into by the first instruction, and then the second instruction need then right after. Question: when will R0 get updated? What stage? After write back, right? So basically, this means that I cannot proceed to the execute until R0 is updated, right? We call this data dependency. Data dependency. And from this example, you have a lot of dependency between all these instructions, right? Here, let's not assume earlier example. Let's assume every stage is one cycle for the sake of simplicity, right? Instruction 1 is the easiest, so I'll do it here. Fetch, decode, execute, memory, write back. All right, I'm done with instruction 1. Someone else fill in the rest. When can I fetch?
6.
Not really. I can fetch right now, right? In instruction cycle 2, I can fetch. I can decode. Decoder then realize, oh, I need R0. When will R0 be available for the decoder? This is where R0 is updated, right? Now, my next question, if R0 is updated, can I go to the execute right away, or do I have to wait one more cycle to take R0 from register to feed into the pipeline register? Okay, right now, if my decoder said I need R0, cycle number 6 is updated. So register file have R0 feeding into the wire, right? That wire go directly to the pipeline register that is between the decoder and execute unit. Yeah. So if I clock, is it okay? Can I move to the execute? Yes. So I can execute here, right? Because wait, actually, I think I'm in a wrong cycle. Let me do it again. Different color for obvious reasons. If I put execute right here, it means that during cycle 5, decoder has the right value for R0. Because that's when instruction 2 can move into the cycle number, move into the execute. It means that within cycle 5, the input to the pipeline register is the correct one, right? Is that the case? At cycle number 5, do I have R0?
Yes.
No, because you have to write enable signal into the register file. R0 is input to the register file. You have to wait until cycle number 6 until register file register R0 new value. So that's when cycle number 6 has the correct value. So, oops, sorry. So you can't do it here. You have to do it here, right? Because at cycle number 6, I have the correct value. I can actually like finish the decoding phase, feed R0 into the pipeline register, but I have to clock one more cycle to move that into the execute stage, right? And then I can do the memory write back, right? And here, right, I can fetch, I can decode here, right? And then I also have data dependency with R3, right? So I don't do anything here until I finish write back, then I can execute. Yes. Why can't I go to the execute, right? So if I want to go into the execute stage at cycle number 6, it means that by cycle number 5, decoding is done. Basically means that by at the end of cycle number 5, the value from R0 need to be into the pipeline register, because if I want to clock to go from 5 to 6, R0 has to go into the buffer of the pipeline register already, right? Over here, right? Cycle number 5, this is the vertical line is pipeline register. It's the input, R0, right? This is new R0. The problem is at cycle number 5, do I have R0? That's still the old one, right? I have to wait until write back is done until R0 is updated. So you have to do it in cycle number 6. So this is kind of like, yeah, you pipeline fetch and decode, but everything is like delayed by 3 more cycles, right? You can then fetch here, decode, right? And then execute, memory write back. The same thing for instruction 5, which will go over the table and we don't have room for that. All right. So again, is this better than 25 cycles if I don't do pipelining at all? Yeah, it's still a benefit, right? But it's not good. Obviously, this is not good. Why do I have to wait 3 cycles to send in this bubble and like not doing anything, right? Now, this thing is called data hazard, and look at this particular problem, right? Data dependency generates data hazard, and it is a really common thing in your program because we can do something like this, right? For I equals 0, I is less than 1000, I plus, right? Look at the value of I update, and then the next instruction I do is I less than 1000, right? See how I do step A, followed by step B right away. I update the value of I, increment I plus plus, the next thing I do, I is less than 1000 or not. That's data dependency, right? So you might be surprised how often this show up. And when it show up, it slows down your pipeline design. And that's the issue, right? It slows down your pipeline design. So if you want to classify the type of data dependency, what you saw earlier called the raw dependency or read after write, and as the name suggests, you're reading something after you're writing something. We call this the true dependency, because in a modern pipeline design, regardless of how you pipeline, you will have this problem. Then there are 2 more called write after read and write after write problems. You will not see these 2 problems with the design we discussed in this semester. But every single CPU that you own will run into these 2 problems, because your CPU, when you have instruction 1, 2, 3, 4, 5, 6, in theory, you're supposed to do 1, then 2, then 3, then 4, then 5, then 6, right? And let's say this is a memory instruction that takes 200 nanoseconds. take a long time. It means that I have to wait for 3 to finish before I can move on to 4, 5, and 6. Your CPU will do this. Launch 1, launch 2, launch 3, while 3 is finishing up. You look ahead and say, can I do 4, 5, and 6? Are there any dependencies? If there's not, I'll sneakily launch them. We call this out of order execution. And as the name suggests, we do this out of order. So in this case, you do 1, 2, you wait until 3 finish. So you finish 1, 2, 4, 5, 6, and then 3. From the programmer point of view, again, it's weird, right? You need to ensure in order write back. But internally, we do a lot of this. When you do this, you have the 2 more data hazards, right after read and right after write. Because you can imagine, let's say this is also the write, but instruction 6 is the second write, but it just happens to finish first. So it overwrites whatever instruction 3 is supposed to do, right? So you have to handle that. Right after read, also again, you write after you read something. If it's like out of order instruction like this, it can happen. Now let's focus on the first bullet. That's the majority of this semester. That's the main focus, the first bullet point, the simple one. Read after write. Read after write. In case of read after write hazard, we need to make sure that, well, obviously, if I'm adding to number, my input should take the right value. And that's it, right? And here's my solution. I know that, let's say I need R0, and I know that I have to wait until R0 is in the register file, right? But is R0, the value of R0 somewhere in my design? I mean, in theory, it's the output of my adder, right? If I can sneakily take the signal from the output of my ALU and plug it in as an input, I'm done. We call this data forwarding. Again, every single CPU do this. The thing is, one thing we can do with raw data hazard, the first simple solution, what we saw earlier, we wait until R0 is updated in a register file. We call this solution stalling. So this is solution 1. Stalling. Wait until I'm good, and then register is updated. That's when I resume, right? This is for the benefit. Simple to design, likely to doesn't have hardware bugs, right? And you might be surprised how many bugs can happen with the other technique. This is simpler, right? From the let's design chip for the first time point of view, this will be like your checkpoint 1 for the pipelining lab. Well, checkpoint 2, checkpoint 1 is let's make sure you can pipeline. Checkpoint 2 is like make sure you can stall correctly. Checkpoint 3 is do the data forwarding, solution 2. Right now, what we do is, well, if we detect data dependency, stall until the data is updated, then I move forward. Right? It's simple. Also, downside, slow. So the question is, can we do better? Right? The question is always, can we do better? And by this point, late second year, early third year, you should always ask this question: can I do better? Right? The idea is called data forwarding. So let's go with the first idea. Stalling. Stalling, somehow we call it insert the bubble. So let's say I have instruction 1 in instruction 1 here, instruction 2 here, 3 here, instruction 4 here, instruction 5 here, right? And over here, I want to do R0 plus R1, right? Over here, it generates R0. Now you see data dependency between instruction 3 and 4. 3 generate new R0, which is used by instruction 4. All right, with me so far? Okay. Now, what happened in the next cycle? Instruction 1 is done. Nothing to do with that, right? Instruction 2 is also moving to the write back. So instruction 2 in the second cycle, instruction 2 is here, right? This cycle 1 to cycle 2. So when we move one cycle, instruction 2 move from instruction from memory to write back. All right. Instruction 3 move here, right? Can I move instruction 4 if I want to stall, if I don't do any data forwarding? I have to wait, right? Because R0 is not updated yet, right? Over here, if you look at R0, it's still the old guy, right? So nothing is sent here. We call this insert the bubble. Why do we insert the bubble? The thing is, you need to make sure you insert something that ALU notice that don't do anything. Because if you insert something that means something else, it might erroneously like put something in DRAM or something that you don't desire. So we insert the bubble, make sure it doesn't do anything by insert the certain signal that if the ALU look at the signal, like, okay, don't care, I don't do anything. Okay. And instruction 4 is stuck here. Instruction 5 is stuck here. Right. The next cycle, instruction 3 is here. In bubble here, instruction 4 is still stuck here, instruction 5 still here, right? This is cycle number 3, cycle 3. Okay, with me so far. Now R0 still not update. Only when cycle number 4, let me put it here, cycle 4, now you have the new R0. You have the new R0, right? Instruction 3 is out, done. Nothing here, nothing here. I can't put anything here in cycle number 4 because in cycle number 3, the input to my pipeline register is still the old R0. So I can't put anything here, right? Again, another bubble. Instruction 4 is here. Instruction 5 is here. Now R0 is the input to my pipeline register. So I can move in cycle 5, right? I can move instruction 4 to here. Instruction 5 to here, instruction 6 to here, right? You see how we actually have to wait one more cycle to make sure R0 is updated, then propagate to the pipeline register. All right. That's inserting the bubble. That's inserting the bubble. Now here's the stall condition. The stall condition is basically it's like the giant if else that you put in at the decoding stage that dictates, can I go forward? All right, it's the condition of can I go forward or should I stall and stay here in the decoder? Okay, so the condition depends on the distance of the dependency. The distance between two instructions that are dependent, in this case, instruction 1 generates something for instruction 2, right? If the distance between the two dependent instructions is less than or equal to the distance between decode and write back, you stall. The idea again is you have to stall until register file is updated, and that's when you can move to the next cycle in the cycle following that. All right, with me so far. Long if else condition. I put it there in case you might want to come back and refer to this. The way you read this is source means that it's the source of my new instruction. Let's say you have instruction 1, which is doing 0 plus 1, right into R2. And then instruction 2 that needs R2. So in this case, instruction 2 has to wait for R2 to be updated, right? So in here, instruction 2 is in the instruction register in the decode. So this is the decode. So if the source of the register that I need during the decode stage equal to any destination of the instruction from execute, memory, write back. These basically the first 3 lines are if I'm dependent on the guy in the execute stage or the memory or the write back, I stall. All right. I stall. This just make sure that it's actually updating the register. Sometimes you have the destination that doesn't really update in this case, it doesn't update R2, then you don't have to stall because R2 will not be updated. Use means that the decoding instruction really need R2 in this case. If it doesn't really need R2, but if R2 is like one of the source, but it doesn't need the new value, you can also move on. Okay. And this is source 1. Sorry, I think that's typo. Source 2. So you need to check both source. If both of the source need something that are being generated, you stop. If I want to classify, right? If I want to classify the type of instruction, you have the compute type, which is the first column. Then you have the memory. So this is compute. This is memory. And this is control flow. Like jump and branch. All right. The compute is simple. If the dependency can come from the decoding stage, I need some value. And that value is only updated after someone else finishes the write back. So the table basically said that these are things that can happen. The load register can also demand something in a decoder because I can have something like this. Load the address at R2 into R3. Basically means that I go to the memory, R2 becomes the address, R2 becomes the address. Then whatever value is in the memory, I put that value into R3. This also means that R3 gets updated at the end of the write back for this guy. And before I can proceed with the load, I need to make sure R2 is updated. That's why I have both the read register, because in this case, you need to read R2, right? And also at the end, it generates R3. So it's basically this is generating new R3 from this example. So the way, again, to read into this table, read means that I might demand this register in the decode stage. Write means that I might update this register at the write back. Okay. And it's safe to resume an instruction only when register is updated. All right. Any questions so far before we go to data forwarding? Actually, I think we might not have enough time. So data forwarding, so the observation is the data is available right after my ALU. Even though I haven't overwrite R0 in the register file, right? The value is in there, in my hardware. So why do we have to wait to write back? Why can't we just use it? The idea is, well, let's just use it. From the middle of my pipeline, take it from there. Okay. So the idea is for each instruction, check if I can forward the data in the future into my input. This would solve read after write dependency. We will go to how we can do this. All right. We'll go over how we can do this in the next lecture. But you can look at this design and see, okay, let's say I have dependency here, right? This one generate R0 and this one need R0. Right. In this case, if I want to stall, I have to wait until write back. For R0 to go from execute, then memory, then write back, then update. But the value is here. The value is actually in this wire, right? Because I just finished the add. I just haven't put it in a register file, right? The thing is, can we cheat? Yeah. The way we cheat is literally connect the wire. Then you select the correct input, right? Then you just need to make sure instead of selecting from the register file, you select that, hey, take that shortcut path from the ALU. So that's the idea of data forwarding. We go into more detail in case like what if the dependency instruction is in the memory or in the write back. How do we do this? Should be less than 15 minutes. Then we go over branch predictor, which is what if you have the branch? How do you handle that? Then on Thursday we go over DRAM. Thursday next week we go over how DRAM works. I really need to ask you to do this. Basically, go get a refresher course on caching by watching the video from SuperScale because that's the material we need for caching. Once you have that, once you know DRAM, once you know the CPU, that's it. That's how your CPU works. All right. Then the following week, which is the last week of class, I think we voted, right? That be a similar format exam. Or do anyone still want to do on site? No. Okay. Same format. All right. Same format. So Tuesday we do a review. Thursday I'll just talk about interesting topic in architecture. Yeah. All right. So yeah.
Project 3 does not require demo, right?
Wait, what?
Project 3 does not require demo, right?
Doesn't require demo.
So project 3 is due on.
Spare me some time to grade. So due on, I would say, I need to check the OAA like final grade submission deadline.
Yeah.
I'll give you guys the tester. You will know if you get a full mark after you run the test.
Wait, so tester.
Yeah, test everything.
Yeah, it's great. It's a tester. By the time the people.
Well, two things. You know if you have anything wrong with different instructions that you have to support, right? Then you can fix it. Then you know how much. Huh?
We will be given the tester while working.
Well, you get the test input of all the assembly that I'm gonna test you with, right? And then hopefully that's enough like information for you to get the full credit on it. Or attempt to get there, all right?
So we set it back on the day finals.
I probably will push it a little bit afterward for project 3, since we're not doing the demo, but I just need to double check like how late I can go.
Thank you, sir.
Have